Hello and welcome to this video about finding the formula of a piecewise graph. In both abstract and applied settings, we sometimes have to use different formulas on different intervals in order to define a function of interest. A piecewise function is a function whose formula consists of at least two different formulas in such a way that which formula applies depends on where the input falls in the domain. A familiar and important function that is defined piecewise is the absolute value function a of x equals the absolute value of x. We know that if x is greater than or equal to 0, the absolute value of x equals x. Whereas if x is less than 0, the absolute value of x equals negative x. The absolute value function is one example of a piecewise defined function. The bracket notation in the definition is how we express which piece of the function applies on which interval. As we can see in the graph, for x less than 0, the function y equals negative x applies. Whereas for x greater than or equal to 0, the function y equals x applies. As long as we are careful to make sure that each potential input has one and only one corresponding output, we can define a piecewise function using as many different functions on different intervals as we desire. Let's look at the graph of another piecewise function and try to find a formula for the function. Determine a piecewise defined formula for the function c defined by the given graph. Notice that the graph is made up of a linear function when x is less than 1 and a quadratic function when x is greater than or equal to 1. Using the bracket notation we saw earlier, we can start writing the formula for c of x by including the intervals for each piece of the graph. So this gives us c of x equals, then we'll have our brackets. I'm going to leave some space for the function formula, but we do know that the linear piece is used when x is less than negative 1, and the quadratic piece is used when x is greater than or equal to, positive 1. And we can identify that the linear piece is defined when x is strictly less than 1 because of the open circle at the right end of the linear function. And we know the quadratic piece applies for x values greater than or equal to 1 because of the closed circle at x equals 1. Now we can focus on finding the different formulas for the pieces of the graph. Notice that the linear function has a slope of negative 2/5 and a y-intercept of 0, negative 1. Using slope-intercept form, we can write the formula for the linear piece as negative 2/5 x minus 1, and that will be defined when x is less than 1. Next, we'll focus on the quadratic piece of the graph. Notice that the x-intercepts are located at x equals 2 and x equals 6. We know the factors will be x minus 2, x minus 6. The only thing left is determine if a vertical stretch has been applied to the quadratic piece. And we can do this in one of two ways. First, starting at the vertex, we notice that if we move left or right 1 unit, the point on the graph is also up 1 unit. And if we move 2 units right or left, the point on the graph is up 4 units. Similarly, if we were to move 3 units to the left, the point on the graph would be 9 units up. This is typical behavior of a quadratic function that has not been vertically stretched. So therefore, we can assume that a equals 1, which we don't have to write, but we'll put it in there. Alternatively, we can use another point on the parabola to algebraically verify or determine the value of a. So notice that the point 1, 5 is on the graph. And so we can solve 5 equals a times 1 minus 2 times 1 minus 6. And simplifying gives us 5 equals a times 5. And when we divide, we find out that a equals 1. So in conclusion, the formula for this piecewise function c of x equals negative 2/5 x minus 1 when x is less than 1, and 1 times x minus 2 times x minus 6 when x is greater than or equal to 1.